All right. You're all very quiet and serious. It's awesome. Welcome to this talk on OAuth security. I'm not sure if you're here for the topic or for the air conditioning, but I'm gonna take both. So now that you're here, I'm gonna teach you something about OAuth security. And if you came for the air conditioning, then well, maybe you'll walk away with some interesting knowledge. And for, of course, people that chose to be here, you know what you're gonna get. And I'm gonna do my best to deliver or meet your expectations. All right. So we have an hour. I need the full hour, so if you're hoping to be out of here in 30 minutes, well, you can, but that's not kind of the way this is supposed to work. We have a lot of ground to cover, and we're going to talk about OAuth security topics. So I'm kind of guessing that most of you are familiar with OAuth 2, which has been around for like 12-ish longer, well, officially around for 12 years, and of course a bit longer when the spec was being developed. If you're doing OAuth today, you're following best practices for OAuth 2. You're using things like PXE and the authorization code flow. And of course, you're aware of the changes that are there for front-end clients and all of that stuff. I'm not going to talk about any of those best practices here today. The talk is titled Supercharging OAuth Security, not just meeting the baseline expectations for OAuth security. So we're going to talk about new stuff. The people coming in, there's some seats left, so don't worry, just run through the room and find your preferred place. We're going to talk about some recently added things in OAuth. We're going to talk about things like resource indicators, which is an older one. We're going to talk about JAR, not the Java thing, but a JOT-secured authorization request. We're going to talk about PAR and proof of possession tokens, like fairly advanced security features, some of which will become the baseline within the next months or years for sure. Others will remain a bit more out there, like if you really need a high security deployment, these are things you might want to look into. No worries, I'm going to explain everything as we go along. Before we do that, I want to set like a very brief baseline, just in case you're familiar with OAuth, but maybe not exactly the dirty details, because libraries today handle a whole lot of that for you, which is absolutely awesome. So what I want to do before we dive in is set a quick baseline of the authorization code flow. I'm going to start with a very high-level overview of what happens. So what basically happens is we have our OAuth client. In this case, it's a backend application running on a server somewhere. We have an API that we would like to access with an access token, and we have our authorization server or security token service sitting right there in the middle as well. So what's going to happen on a very high level, the backend, the client, OAuth client, is going to run an OAuth flow one way or another and is going to obtain an authorization code. That's essentially step number one. Step number two is we're going to exchange that authorization code for tokens, and step three is we're going to use that token to access that access token to access an API. All right? So if you've been doing OAuth, you know that this is the worst oversimplification you can ever come up with, as in these three steps, in reality, they're like, if I would split it out fully in a slide, which I do in my more in-depth courses, we would have like 15 different steps to get that done. And the bulk of the meat is in step one here. That's where we have all of the interactions through the front channel and the redirects in the browser and so on and so on. We're going to talk about these details quite a bit today, so what I do want to do here is I want to split it out just a little bit, show you a little bit more detail, while skipping over certain aspects. So for example, I'm going to skip over PXE, proof key for code exchange. It's a best practice, it's something you should be doing, but seriously, I would need at least 5 to 10 minutes to fully explain how to do this correctly, and it will create more confusion than it does good. So I'm just going to omit it for brevity reasons, not for you shouldn't do this reasons. So what's going to happen is at some point, and we'll see that in one of the demos, there's going to be a start of the flow. So the user typically is going to signal that they want something to happen. They want to connect to accounts, or they want to maybe log in if you're doing OIDC and OAuth together or whatever. And that's basically going to be the signal to start. Come in, there's seats left, so if you don't mind crawling up the stairs, we have fresh air upstairs as well, so that's awesome. So the user is going to initialize something, and then we're going to start the flow. So the OAuth client is going to initialize the flow with the authorization request. That's basically step number two, which is your traditional redirecting the browser to your security token service, to your authorization server, to follow that request. That's the request with all the flow configuration parameters and so on and so on. And that security token service, if there's no active session going on, doesn't know who you are, it's going to be like, dude, I need some authentication. Who are you, please? Can you log in? That's where you get the login screen, and you log in with username Philippe and password, the name of your dog, for example. That's not my real password, by the way, so don't try this on my accounts. It's just an example. And my random number is always 17, by the way. So when I'm teaching with random numbers, it's always 17. That's the user's ID. Anyway, the user authenticates. The authorization server is pretty happy. It's like, oh yeah, we know Philippe, and yeah, all of this makes sense. And it's going to issue an authorization code. That's the redirect back, calling the redirect URI on the client. The browser is going to follow that, which delivers that redirect, that authorization code to the client application. All right. Next step, the client is going to exchange that code for tokens. That's a backchannel request. It's a fairly simple post call to the authorization server with the authorization code and some other parameters, including client authentication. And the response is going to be tokens, typically an access token, a refresh token, maybe an identity token, depends on what exactly you are running. But in our case here today, we're mainly interested in the access token for whatever use cases we're going to talk about. And with that access token, we can access the API. All right, so that's essentially what this looks like. If you want to make this a bit more nerdy, I have some monospace fonts as well. So this is the actual request being sent in step 2 and 3, the authorization request, which is kind of important because we'll talk about that for the majority of the topics here today. And you'll see that there's all of the different parameters there. Line 2, response type code, meaning we're running an authorization code flow. We have a scope in there, client ID, redirect URI, and some PXE parameters, as you can see right here. All right, that's essentially what the authorization code flow looks like. Terminology-wise, if you're like, yeah, this is not really spec-compliant terminology, you're absolutely correct. Good for you for reading the specification. The real problem is I do a lot of these presentations, a lot of these talks and trainings, and what I'm often struggling with is when you are talking about OAuth or OpenID, the terminology would change based on the spec, and it's like a big mess. So I've settled on this common set of terminology, which covers most use cases we see today. But if you want to translate whatever I'm talking about back to the spec, this slide will provide you with that mapping. All right. So before we dive into the dirty details, small word about myself. I'm Philippe De Ryck. I'm kind of a regular at NDC events, but my first time here at the Developer Festival in Copenhagen, so that's really awesome. Looks like a beautiful event here as well, and I hope you're having a good time. I'm a security expert from Belgium. I did a PhD in web security like a long time ago, really deep into cross-site request forgery and such. And today I run my own company called Pragmatic Web Security. And that's a very deliberately chosen name. I help companies figure out security, make trade-offs, identify not the ultimate super best practice, but the best practice that works for their use case in their scenario and how they can make things work. That's essentially how I spend my time. I help developers with training, like I did a conference workshop here 2 days. Some of you were at the workshop, so they were not tired of hearing me speak, so that's good. Good to see. I also do a lot of in-house training, online courses, and so on, and also expert consulting. So if you need help with OAuth, OIDC, especially figuring out how to do things in more complex scenarios, you often end up with me. So if that makes sense, keep that in mind. I'm a Google developer expert. Side note, this is an outreach program from Google to recognize the work I've been doing in the community, like talks and cheat sheets and articles. So I don't work for Google. They just send me free swag every now and then, and I mention them, and that's kind of a symbiotic relationship, so I'm not complaining. And then finally, I organize SecOpDev, which is a week-long AppSec course in Belgium. So if you ever need a good reason to visit Belgium, preferably on the dime of your employer, that's SecOpDev. So runs in June next year. So take a look in like half a year at the program and see if you want to join Belgium in June. I can't promise good weather. It's probably the same as here. It's like either very bad or very good, and we don't really do in between in Belgium. So very unpredictable as well. If you want to grab a copy of the slides now or later, you can find that on my website. It's not that hard to find. The QR code is a direct link, so I'm going to give you a second to scan that while I'll prepare myself to dive into the dirty details of OAuth security. And of course, if you want to connect on LinkedIn later, always highly recommended, so you can stay up to date with whatever I'm doing. All right. Always a good idea to just blindly scan QR codes in a security talk. So, or on a restaurant table or whatever. It's like we're throwing all these best practices for security, like always be careful with your whatever, scan it and let's go. But trust me, it's fine, no worries. All right, enough laughing. Let's get a lot more serious and let's talk about OAuth security. first topic, I have 3 main topics. First topic is reducing the power of access tokens. And one of the challenges that we see there is very often when you start out with OAuth and it's like a textbook example, you have one client and one API and you're very happy and it's like very logical and everything works. And then you deploy this in like a real world application or scenario and you start to have like a lot of clients and a lot of APIs, and very often one client needs access to multiple APIs. That's a very common scenario. What does that mean concretely? That means concretely that you probably have an access token with a lot of authority. Like one access token that you've obtained from your STS, and it gives you access to like the reviews API, if you talk about restaurant reviews, the restaurants API, and maybe the admin API if you're an admin, and like you have a very, very powerful access token. By itself, maybe not the biggest problem, except what happens when the access token is compromised? What happens if somebody gets a hold of that? It's like, ooh, this is valid on all these locations. That might be a bit of a problem, especially in a high security deployment, financial APIs, eHealth apps, stuff like that. That's probably not something you want happening. So what you often see in tokens depends a bit on the implementation. Some STSs, they use audiences specifically in their token. So you have a list of audiences advertising basically where this token might be valid. It's like, oh yeah, you can use it for this and this and this. Interesting. And if you don't have the audiences, this is not necessarily spec compliant, even though some implementations do it. You also have the scopes, and scopes very often identify an API specifically and then a sub-permission on the API. So that scope list would also identify where you can apply this access or use this access token, what the authority is of this access token. And then finally, in more advanced use cases, you might want to encrypt your access token so that nobody in the middle can even identify what's in there, and the API can decrypt that. But decryption works with a private key, and doing that with 3 different APIs for the same access token, that wouldn't really work well, because the private key is supposed to be a secret, and if you share a secret with 3 different applications, it's not really a secret. It's like a shared variable, but not a secret anymore. So all of these challenges have led to the inception of a new spec. Well, new is relative, like 4 years ago it became a spec, but fairly new spec. And that spec is called resource indicators. And resource indicators is a way for the client to make things better by requesting individual access tokens per API. So basically, if you want to access 2 or 3 APIs, you're going to do some magic in the OAuth flow, which I'll talk about in a slide, no worries. Do some magic, and that allows you to say, like, now I want an access token for API 1, and now I want one for API 2, and you get like 2 or 3 access tokens, each with 1 audience, and that allows you to have access tokens with minimal authority. Also prevents abuse if one is stolen, prevents one API from using an access token and using it on a second API, and so on. So it makes things a lot better in general. All right, so how does that work? Well, it's actually fairly straightforward. Behind the scenes, there's 2 major changes. Major change number 1 is when you initialize your request, when you do the authorization, initialize your flow, the authorization request, you have to signal to the STS which resources you would like to access, which APIs you would like to access. And you do that by including resource parameters, as you can see on line 5 and 6. So you're basically saying like, hey, I'm this client, and I would like to ask permission to access API with reviews and API with restaurants, in my restaurant review example. And this allows the STS to evaluate that request for one. If there's user consent involved, it allows them to pop up the consent dialog saying like, hey, this application would like to access reviews and restaurants on your behalf. Do you want that? And so on and so on. All right, that's major change number 1. Second change, this is not defining which access token we'll get. This is just listing what authority we would like to request. And now we have to ask for a specific access token. And that happens in this diagram on step 8, like the exchange of the authorization code for tokens. That's where the client now signals, like, before I asked about some APIs, now I would like to receive an access token for this specific API, this particular one. And again, that's a resource parameter. That's a new one with resource indicators. In line number 7, we ask for this specific API. All right, and that's essentially tells the STS like it's going to issue an access token and it's going to use only this single audience as the audience of that access token. So if you look at the actual access token, you will now see in the access token there's some claims. I've not listed them all, but you'll find that there's now an audience claim, which used before was like custom implementation of spec. Now there's a spec that defines the audience claim, and it has a single value specific target audience, which reduces the authority of the access token and also ensures that if you want to encrypt it, you encrypt it so that only the reviews API would now be able to decrypt it. And you include the subject in there as well, and the scopes are there as well, just like in any regular OAuth flow, except that the STS has now applied downscoping. As in, it wouldn't make sense to include scopes for different APIs because scopes are linked to an audience typically in the configuration. So now it only includes the relevant scopes for this particular API. All right? Problem? We asked in the beginning for 2 APIs and we only have an access token for 1 API. We can't exchange the authorization code again because that's not how things are supposed to work. You're only supposed to do that once. But the next token can be requested with a refresh token. So if you also get a refresh token, well, you should also get a refresh token in this case. And now you can run a refresh token flow, and in that refresh token flow, you can include another resource parameter and saying like, I would now like to request an access token for the other API. And the STS will evaluate that request, issue a new access token with, again, a specific target audience, and so on, and so on. And that is, in a nutshell, what resource indicators brings to the table. I know I'm not going, well, I'm trying to give you as much detail as possible. All of this is from the perspective of a developer, by the way, because those are the people that need to use this. So we can talk about the implementation details on the STS side, but that would be for after the talk during one of the breaks because we can't go into that much detail. Good. So resource indicators, really useful spec, especially if you have an architecture where clients need to access multiple APIs. It probably makes, if you look at the security of that system, it probably makes you a little bit uneasy that you have like these super powerful access tokens. And this is something that can definitely help in reducing the authority of those access tokens. All right? Proof of possession is even better, but we'll talk about that towards the end of this session. Good. One topic down. That's awesome. We have 2 more to go, but it's going to get like gradually more complex. So hopefully you'll bear with me as we go along. Topic number 2, securing the authorization request. All right, that request with all the parameters, there's some issues with that. So if you look at the OAuth flow in general, here's that request again, but if you look at an OAuth flow in general and you look at the evolution that has happened in the last like 8 to 10 years, you'll see that it has evolved quite a bit. Like we have deprecated some flows, like the implicit flow, like, yeah, stuff going through the front channel, we don't really trust it, so just use the authorization code instead. That's a lot better and cleaner. And we have added PXE to the flow to ensure we can protect the flow integrity. Like PXE helps to ensure that the flow can't be interrupted and continued somewhere else, and so on. And then we have the authorization code, has always been well protected, like one-time use only, short-lived, and so on and so on. And in all that story, in that whole story, we kind of ignored, well, ignored is a big word, but I'm not sure if it's fair to say it that way, but security of the authorization request has been neglected, let's put it like that. It's always been something that has been there that we never really liked, but it is what it is, and it never really got to the point of being more secure. So what that basically means is in step 2 and 3, where we initialize the flow with all of these parameters, we have cases where the attacker can tamper with those. Imagine that you're a malicious user and I'm building the app and I'm sending that authorization request through your browser. Nothing stops you from saying like, hold on, I'm not going to follow that redirect. Tool like Burp makes this super easy. I'm going to stop that redirect in my browser. I'm going to look at that and maybe I'll change some parameters. Maybe I'll ask for more scopes. Maybe I'll change the redirect URI. Maybe I'll remove PXE and see what happens. And this basically allows an attacker, a malicious user, to violate the integrity of the flow. This is not earth-shocking news. This is not like a new revelation of an attack against OAuth. This is something that has been on the agenda for like 4 or 5 years, definitely, where the OAuth security best practices, which is almost an RFC if I'm not mistaken, already highlight some of the dangers here. So we see specific guidance in that document saying things like, attackers can abuse the redirect URI, should only do exact matching, because if you have like patterns with wildcards, somebody can give you a malicious URI, and then the authorization code goes to the wrong place, and so on and so on. That's something what an attacker can manipulate when they see traffic in the browser, when they intercept the URI, and so on and so on. Also, you'll find things like a PXE downgrade attack listed there, which is basically where the attacker tries to not use PXE even though the client wants to, and that would allow them to launch other very complicated attacks and so on. Now, these things are like security considerations. So roughly speaking, that means somebody was sitting behind the computer and thinking like, what can go wrong? And they wrote something down in the spec and so on and so on. But you also see these in practice. Like these are based on real world attack scenarios. And you see vulnerabilities in products like Keycloak, not a dig at Keycloak in any way, just a simple example of how they had that redirect validation vulnerability in their product. All right, so this is definitely something we have to worry about. If you want a seat, if you want to stand up, that's very healthy. So by all means, do that. If you want a seat, we have some seats available as well. So don't worry about disturbing. Just come in and enjoy the rest of the talk. All right. So the authorization request. What can we do to secure this? Two options: jar and par. And this sounds like a Star Wars thing, but trust me, it's going to be about OAuth, all of these weird abbreviations. JAR is about JOT Secured Authorization Request, all right, which is a very, very complicated term, but if you translate that, it's like instead of putting all of these parameters in the URI, what if we put them in a JOT? Which may trigger the reactions like, seriously, another JOT, like, do we really need that? But one of the benefits of a JOT is that it's signed. The client can sign the JOT, and if the client signs the JOT, nobody else can change one of the parameters, because then the signature becomes invalid. And now we can protect our parameters, prevent tampering, especially from someone in the front channel. Once the URI leaves the backend and is transferred to the STS, the authorization server, somebody can tamper with that, but not if it's a JOT. How does that work? Well, it's actually not that hard. Here's the updated flow. The things in green have been modified. So it's only 3 modifications, fairly straightforward. Step 1, or modification 1, step 2, is the client now generates a JSON web token with all the flow parameters. That's essentially what's going on. The client is basically going to be like, oh, you know what? I'm going to generate a JOT and put all of my flow parameters in there, and I'm going to sign that. And the client is going to send that JOT in the URI to the STS. So the URI is now changed. Instead of all the parameters, it contains 2 parameters, a client ID and a JOT. And it goes to the STS, and the STS will verify that signature of that JOT, and then looks up the claims, and it's like, oh, you want to run that flow. That's basically what happens in practice, and this is a very, very good way to address these issues. So what does it look like in practice? Here's a step, the authorization request, basically, and you see that we now have a client ID in there, which is kind of mandatory in OAuth flow, so that's why it's there. Otherwise, we could even skip that, but it has to be there. And we have a request there, and the request is the JOT. It's a configuration of the flow encoded as a JSON web token signed by the client. Of course, to make this happen, you also need to set up key configurations. So the client needs to have a private key, which you register with a security token service. So somewhere in the configuration, you have to say, like, here's the client's public key. It's a bit messier than a client secret. It's also a lot more secure, because you can now also use key-based client authentication, which is kind of a recommended best practice anyway that we're not going to talk about here today. So if you already have key-based client authentication, then setting up this is super straightforward. All right. Awesome. Benefit here, the JOT is signed and prevents tampering with parameters. Very, very important. All right, so what's in the JOT? That might be very interesting as well. The way you can recognize a JOT, by the way, a JOT has 3 parts with dots in between. So if you look closely, you'll find some dots in here. And it's base64 encoded each part. And just a small trick, if you want to recognize base64 encoding, look for the EYJ. Whenever you see EY and then capital J in a string, that's the base64 encoding for the curly brackets with a new line. It's like, aha, bam. So whatever you find with EYJ, throw it in a base64 decoder, and magic happens, and you find something like this. So the JOT is well defined in the spec. It has a header with some claims, and it has a payload with very familiar claims, because the claims of the payload are basically our flow configuration parameters that we previously put in the URL. Like literally all of them, take it from the URL, drop it in as JOT claims, and off you go. So very concretely, what we have there is we have an issuer and an audience. These are JOT-specific claims that were not in the URL. It's basically a good way to prevent somebody from misusing this JOT in other places. So it basically says the issuer is the client, that's a client ID, and the audience is our authorization server, or STS. All right. Next up, we have our client ID is in the JOT as well, must match the client ID that we put in the URL. for obvious reasons, but it's a very important check to do. And then we have all of the other parameters that we used in the request URL, including potentially resource parameters if you're using resource indicators as well. Anything you would have put in the URL, you now put in this object. The header, very specific as well, follows job best practices, like a specific type for the header, which is OAuth auth plus JWT. It's registered, so it's not something I made up. It's something that the spec defines and has registered as a known type. And then we provide a key in case the client has multiple keys. The STS can use this key ID to find the right key to verify the signature on this specific object. All right. Awesome, right? Well, I think this is pretty cool. Things are going well, so time to challenge this and try to do a live demo. This is always where things blow up, so if they blow up, my apologies. This is not intentional. I do my best to not have that happen. But guess what? Sometimes it happens. So let's tempt the demo gods and see if we can look at jar in action. Before we do that, small thing about expectation management. This is not going to be the world's most exciting demo. Just so you know, we're going to be running an OAuth flow. It's going to be very, very non-interesting, but I'm going to try and show you jar in action and also show you how you might implement that in your application. So what we have here is we have a very simple demo with a Node.js backend, and what we're going to do is we're going to launch an OAuth flow like I showed you on the slides, right? And if I click on this, it will take me to the login page. I'm going to use Identity Server as an example because you can use it for free for testing. It's pretty good. It has all of these features, and it runs locally, so it checks all the boxes for demos. So it takes us here. We can log in as Bob with a very secure password. I'm going to let you guess what that one is. And then we can go, we come back to the application, and nothing happens, basically. All right. By design, I must add. So behind the scenes, here's the terminal of what's going on. You see a little bit more output. We're nerds at all, so this is good enough as UI. You see the redirect going on here. This is a traditional authorization code flow, right? This is just an authorization request with all the parameters in the URL. We run this one. We have received and validated tokens, and you can see there's an ID token, access token, whatever is going on. All right. We can also see this in the browser somewhere. Let me see if we can find that. Right here is the authorization request, and you can see that this is basically our traditional authorization code flow. Let's change that by implementing jar. I'm not crazy, so I'm going to do live code. Well, I'm going to do some live coding, so bear with me. I'm going to comment this and uncomment that. So that's as far as I go with live coding. So authorization code flow with jar. I've done all the work up front. So what we're basically going to do is we are going to use a library. I'm going to use OpenID client for Node.js, which is actually quite good. It has some quirks I don't like necessarily, but it implements jar and par for that matter, and it's actually quite a decent library. So what are we doing here? Well, with jar, we are creating a request object. That's the bulk of it. We're putting all of our parameters in that request object, just like we previously would have done for our URI. So we include some scopes, the redirect URI, the Pixie stuff, and so on and so on. And then we're going to use create the authorization URL. I'm going to do some line wrapping here. Authorization URL, this is a manual operation. The library can do it for you, but it also keeps all the other parameters in the flow. And I don't think it's clean, I don't think it's pretty, so I prefer to only have the two parameters that we need, the client ID and the request object. So you can see here, we add the client ID right here, and we add the request object right here. That's it. So let me save this, and let's run the example again. Clear. Of course, we're not going to have to log in here because we are still Bob, but you can now see that our request URL is changed. Now we have a client ID parameter and we have a request parameter. And this is the job right here. So let's see if we can actually grab this and decode this. No. That's why I don't do live demos. I mean, who here uses this website? Yeah. They're reworking it. They're going to change it. there's like this warning. I saw this last week. I was like, what? So I hope that they know what they're doing and not killing their golden goose, but we'll see how that goes. But yeah, this website must see insane traffic, by the way. Here's the details. You can see that this is now, the type is right there, the JOT type, and then all the parameters are there in the JOT. And this is basically how jar works. The STS, the identity server instance, is configured with the public key of the client so it can verify this JOT, and so on and so on. And that's basically how you use jar. As you can see, it's not a very heavy lift. It only changes something in the client where you start the flow, and that's it. All right? Good. Brings us to a takeaway using jar. Jar is actually really good. It solves a very specific problem that is a bit of a silly problem to have, as in we've done so much to secure OAuth flows, then having these unprotected parameters just there for tampering in high sensitive applications doesn't really make much sense, and that's why jar has been added to eliminate this insecurity. All right? Now that I've explained jar and that you have captured everything, I'm going to talk about par, which kind of makes jar irrelevant. So sorry for wasting 15 minutes of your time. No, that's not true. No, it is true, but jar has its uses, and jar is very useful, but I would say if you can, you probably want to use par instead, because par is even better. Like if you think that jar is awesome, you're going to be like, whoa, par is even better, awesome. So what is par really about? Pushed authorization requests. Par has a lot more impact on the flow. So much that I have to redo the entire flow with par enabled. Again, I'm going to skip Pixie, but I'm going to try and explain how par works. In par, we're going to not send anything in the front channel, or almost not anything. Like not even a signed object, just nothing, except an ID. We're going to tell the STS, like, we're going to run the flow with ID 17, please. And STS is like, okay, of course we do. And that's how it works. How do we do that? Well, we do that by pushing our authorization request, like our configuration of the flow, to the STS before we start. So the user is like, hey, I would run an OAuth flow, and the OAuth client is like, yeah, that's good for me. I'm going to tell the STS what I want to do. So this is a new type of request, a par request, and we're basically pushing our entire configuration to the STS, saying like, hey, in about 2 seconds, I'm going to be running an OAuth flow with this configuration, and so on and so on. By the way, I'm this client. What do you think about that? And the STS will evaluate that and make sure everything makes sense and checks out, and so on and so on. And if everything checks out, it gives us an identifier, a par ID. Come in, there's some seats at the top, so just use your elbows to find some place, and you should be all good. So what we have here is we have a par ID given to the client, and that par ID is what we will include in the authorization request. So basically what we're doing is we're telling the STS, like, hey, we're going to run a flow, and we're going to use this ID of the configuration that we gave you earlier. And the browser is going to follow that redirect. The STS will look up what this ID is, like, oh yeah, this flow configuration, and runs the flow as normal. Like, who are you? Please authenticate. Yeah, my username is Bob, password Bob, and off we go. And then we get an authorization code, and now everything runs as normal, just an authorization code. We exchange the code for tokens, and we handle the tokens however we see fit for whatever we're trying to do. That's par. The green ones are the modifications in this flow. What does this look like? Well, we have a new request. We have a par request now, and that goes to a new endpoint, the par endpoint. So an STS that supports this will have a par endpoint. It's going to be listed in the discovery file. So if you load the discovery, there's going to be like par endpoint and par support and so on and so on. And now you send a post request there, back channel communication with your flow configuration. All right? Just like everything that you would send before, you now send to that par endpoint, including a client secret or a signed assertion, or however your client authenticates. This is an authenticated endpoint, which basically means that the STS can upfront verify who the client is, verify if everything here is valid, and if the client is like asking, by the way, I'm going to try to access the admin API, and STS is like, the hell you are, then it can, at this point, can already say like, go away. No par ID for you, bad client, 400, something, and the client goes away, doesn't get a par ID, and can't launch a flow. That's basically how par works. What's the response? If everything checks out and you do get a par ID, you get a simple response. It's a JSON response with a request URI, which is a very complicated way of sending an ID. It's a URN, blah, 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 with a specific ID. So the first part is like static junk because of RFCs, and then the last part is the actual ID generated by the STS. There's an expiration time, which is 60 seconds, which should be enough for any client to figure out how to start an actual OAuth flow and follow the redirect. Of course, if you're dealing with like super slow clients, you can make this a bit longer, but there's really no reason to do that. And that's essentially how the first interaction works, the PAR request and PAR response. Next step, run the actual flow. There's two parameters. I'm going to let you guess. There's the client ID, yes. Well, it's there already. And the request URI. All right, good. I wasn't actually expecting a response because we're like in close to Scandinavia and people do not interact in Scandinavia. So the higher north you go, the quieter the room gets. And teaching a workshop is always very interesting because it's like, what do you think about this? Everybody's like, if you pull hard enough, it works. So thank you for playing along. Absolutely appreciate it. So the client ID is there because it has to be there, OAuth specific reasons, and then the request URI containing that PAR ID is there as well, and that's essentially how we launch the flow. And that's how things have changed, and this is a change for the better, by the way. This removes any sensitive information going through the front channel. Even in a signed version, nothing. There's no attack vector left. The only thing the attacker can do is maybe inject a different PAR ID, but even that is not really going to work well in practice. And with the short-livedness of these PAR IDs, there's not much viable attack vectors left. So this is really good. And I'm going to give you a demo. Crap, now I have enabled the interactive mode. So I wasn't going to discourage you. Maybe I was. No. Let's do questions at the end. All right. I'll promise to try and finish 5 minutes before the end, and then we'll do questions as much as you want. All right. PAR demo. Hold on, because this is going to be super awesome. We're going to comment our jar line and uncomment our PAR line, and off we go. So what do we do in the PAR function? The library handles most of this for us. This is actually really awesome. I didn't even have to send a request to push the authorization configuration. I was like, whatever, the library handles PAR, so we do client pushed authorization request, provide some parameters. The client sends the request, gives us a response, tells us what the response is, and now we can include the client, the request URI right here in the URL along with the client ID. Again, you can ask the URL from the library. It does include all the other parameters still in the URL. I don't think it's very pretty. I told the author and he was like, yeah, I know, but for practical reasons it's there. It doesn't matter. I was like, yeah, I don't like it. And that's where the discussion ended. Which is his total right, by the way. It probably doesn't have a negative security impact. It's just, it doesn't have to be there. So that's why I mentioned this in the code. All right, so let's see if we can see this in action, right? It's running. So we go here. We clear this, and we launch our OAuth flow again. And there we go. What do we see here? Well, we see the client ID in the URL and the request URI. This is the PAR ID that has been generated by our security token service, and that's the one that we have to send when we start a flow, as you can see here. You see nothing else, by the way. Why? Because this is a back-channel request. It's Node.js to the STS. The browser isn't in the mix, so you can't see that in the browser's DevTools. That's why I have some very useful output here somewhere. You can see I'm a really good developer as well, by the way. My apologies for that. I'm going to make a note to fix that. So we received a PAR response. As you can see, there's like a lot of useful information in that PAR response. And that's a good thing that this is recorded, so that's awesome. Seriously, do not hire me for your development purposes. And that's the URL that we have used, and you can see that we again receive tokens there as well. So very simple, very straightforward. Changes needed on the STS, of course, but also only on the client and only during the initialization of the flow. So modifying your clients to start using PAR should be fairly simple and fairly straightforward. All right, very localized changes, and there's library support for this. And somebody told me, like Anders told me, that .NET is supporting this as well, and will make this the default for OAuth flows, which is really awesome as well. Yes. I'm not an AS.NET guy, so I have no idea what that means, but version 9. So, all right. Good, good. Exclamation mark. This is an important notice. If you want to use PAR for certain clients, you can configure them, you should configure them to only use PAR. Because otherwise, if you enable both modes, then the client could still use the old one and it can create confusion, or maybe there's certain scenarios where somebody does the wrong thing, so you can configure your STS to only allow PAR, and then if the client tries to run a normal flow, it's going to be like, use PAR instead, and this would be better. So that's a configuration step that you should not forget when handling PAR. All right, brings us to a takeaway. Pushed authorization requests eliminate the need to send all of these parameters over the front channel. We do it with a back channel request instead. Really, really big step forward. I'm a big fan of PAR, and in general, it is a good thing. I envision that PAR becomes a recommended best practice really fast, by the way. So the recommended best practice for authorization code flows is not like Pixie with all the parameters, and I can imagine that there's going to be like a consensus, like, yeah, let's just use PAR for everything. And the .NET News, as Anders said, like right before my talk, is evidence that this is going definitely that direction. So that's really awesome to see. If you really want to, you can combine PAR and jar, right? So you could generate a jar with all your parameters, sign it, and then send that with PAR to the STS. In most cases, I would say that's pretty overkill, as in you're signing something which is going to be sent over a direct server-to-server HTTPS connection. Probably that's not going to be necessary, but there might be cases, maybe there's proxies in the middle, maybe stuff you don't trust. In that case, you might want to opt for using both together, but that would be the odd case, not the default use case for this. All right? Good. One more topic. Sender constraint tokens. Who here is using bearer tokens? Yes, everyone. Awesome. Normal response, by the way. It's the default, it's what everybody's using, and quite frankly, it's surprising that we haven't fixed this, because we can fix this. It's actually quite possible to fix it. It just takes a bit of, well, not a lot of effort to do that, but the security benefits are massive. So what's the problem with bearer tokens? The meaning of a bearer token comes from like the bearer, the holder of the token, has the authority to use it. It's like bearer bonds, like if you have the papers of whatever money thing you have, then you're the owner of that. So if somebody steals it, they can use it. It's like their money now. And the same thing holds for these tokens. If somebody steals your bearer token, it's their token now. They can do whatever they want with it, and they can abuse that. How does that happen? Well, somebody can get it from your client. Maybe somebody breaks into your client, steals an access token. If you send it to an API, the API has it. Maybe the API is compromised, maybe it deliberately becomes malicious. It now gets an access token from you and can be like, oh yeah, awesome, turn around and use it somewhere else as well. And there's various other cases how access tokens can find their way into the free world and be abused, basically. The solution for this is to move towards what we call sender constraint tokens, which what we're going to talk here are proof of possession tokens, basically. Tokens that are no longer bearer tokens, but a token where you need to prove possession of a secret to use it. This means if I have your proof of possession token and I send it to an API, the API is going to be like, you have to prove possession of a secret, which means I would also have to steal a secret from you, which is a lot harder typically. It should be embedded in like a key vault and so on and so on. So it's a private key, and unless the attacker also has the private key, they will never be able to use an access token that is linked to that private key. That's essentially the concept of proof of possession mechanisms. And there's two ways to implement that. There's the old way, and there's the new way. Awesome. The old way, everybody's going to be like, bleh. Even though it's super awesome, it's super simple, it works really well, and you have to implement virtually nothing for that, people still don't like it. The old way is MTLS. So mutual TLS, where you use like TLS certificates on both ends. I see some people shaking their head like... It's basically where you use like certificates on the client, certificates on the server, set up a TLS connection which is mutually authenticated, and your token is going to be linked to that certificate and that certificate alone. Meaning if you don't use that certificate to set up the connection, with of course the corresponding private key, the API is going to be like, not good enough, go away. And that's one way of doing that. Why is this super easy? Because MTLS is implemented in every single networking library you can find. All it takes is like 2 lines of configuration, like here's my cert, use it, and you're done, basically. That's how simple it can be. Of course, you have to generate the certificates and manage them and so on, which is a bit less pretty, but implementation-wise, it is really, really straightforward. How does that work? Well, of course, we have the normal server TLS cert. We don't care about that for this specific slide. But the client has their key pairs. Where's my highlighter here? The client has a public and private key and a certificate, and the server, the STS here, also has that certificate and of course the public key, which is kind of embedded in the certificate. So what's going to happen is we're going to set up a MTLS connection between the client and the STS, and we're going to exchange the authorization code over that connection, which will give us tokens. And when we do that, the STS is going to generate the access token, and it's going to put the fingerprint of the certificate inside the access token. So now we have an access token that is sender constrained for a specific TLS certificate. And you can only use that certificate if you also have the private key, which nobody else has but you. So whenever the client now accesses the API, they use the same MTLS certificate to set up the connection, same private key. The access token goes to the API, and the API will verify that. The API will be configured to look in the access token. There's like a CNF claim now with the fingerprint, and the API is like, ooh, it's going to take the fingerprint of the cert, that fingerprint, compare them. If they're the same, good. If they're not the same, go away. And that would be a 403 or whatever you're doing there. 500 also works really well for error messages. That's basically proof of possession through MTLS. Super simple, super straightforward, and your networking library does the heavy lifting. So if you can, I'm going to recommend to use this because it works really well and it has 0 effort, implementation-wise. What does a token look like? There's going to be extra claims in the access token. There's going to be the CNF claim confirmation with an X5T, X5 thumbprint in the SHA-256 hash format, whatever fingerprint is there. The API has to check that. Of course, it's up to the API to mandate that if this claim is present, to ensure that they check it. Otherwise, there's no point in having that there in the token. All right. Awesome. That's the old way, so whatever. Why is there a new way? Because MTLS doesn't always work. All right, MTLS, maybe you don't want to implement that, maybe you can't implement that, maybe managing certificates is too hard, maybe the infrastructure is too complicated, maybe your API is like 18 hops behind some gateways and reverse proxies, and it's just a big mess to forward all of that information, and so on and so on. If that is your case, or if you simply don't like MTLS, that's also a valid reason, then you might want to learn about DPoP. And DPoP is a new mechanism called demonstration of proof of possession. And it's basically the same mechanism, but on the application layer. It's the same mechanism, but now you get to get the joy of generating JSON Web Tokens and signing them and exchanging them and including them on the requests and so on to prove that you possess a private key. So it's basically like MTLS with a lot more work. Well, no, it's not true. It's more flexible because it's application layer. It gives you more flexibility. You can do it in various use cases where MTLS wouldn't work well, but it's a lot more work to get this done. There's a spec for that, fairly recent, from last year that was finalized, and I'm going to walk you through DPoP. And it's going to take me like 15 slides to do that, because there's a lot of dirty details that you have to take into account. This is going to be a super wild ride, so stick with me. I'm going to be as brief as I can to try and explain this. It's not that complicated, it's just that there's a lot of tiny things that you have to match together and handle. All right, so what is the setup? We have a public-private key pair on the client. You can generate these on the fly. You don't have to distribute them up front. You don't have to register them up front. You can do this on the fly, which is actually kind of awesome compared to MTLS, one of the benefits. When we want to exchange our authorization code, we have to generate a Deop proof first. So we're going to prove to the STS that we possess the private key, so they can use our public key to link the access token to that. All right, so we generate a Deop Proof. We send that to the STS along with our authorization code and our public key. The STS will verify all of that, of course, and then it will generate our tokens. It will generate the access token, maybe the refresh token as well. It binds them to the public key that we just provided. And it sends us the access token, refresh token, and so on. Now we want to use that access token on an API. Not so fast. First, we have to generate a Deop Proof for the request we're going to send. Deop Proof specifically linked to this request. That proof will be included along with the request and the access token, and the API will have to verify these steps. The API will verify the Deop Proof, verify that it's linked to the access token, that it matches the request, and so on and so on. More details will follow in the next slides, don't worry about that. This was only one slide of the 15. And that's how Deop is going to work in practice. All right? Like I said, a bit more work, but it gives you proof of possession semantics for scenarios where MTLS would not be feasible. All right, let's look at the dirty details. What's going on? The first Deop Proof. That's basically to exchange the authorization code. It looks like this. It's a JSON web token. So you're going to be generating a whole bunch of JSON web tokens. There's a header and a payload, and you can see the specific values. There's a type, DPoP plus JWT, again, registered. We include the public key inside the header. That's the key of the client that was generated on the fly. We include a unique identifier to prevent replay attacks. We include the type of request we're going to send, a post request to a specific URI, the token endpoint, and that's basically the relevance parts, and all of that is signed by the client's private key. All right, that's a Deop Proof. This can only be used for this particular request. There's an issued at timestamp, so the STS can reject things that are too old, that it doesn't like maybe things that are older than 5 seconds, go away. We don't need that. And that's the proof that's going to be sent along with step number 3 as follows. So that request looks like this. It's an authorization code exchange, so it's a post to the token endpoint. We include, well, actually I have some text here, so I'm going to just use the text. It's a traditional request, but now we have a DPoP header. And that DPoP header is a new request header. It includes the proof that we generated just before. All right? The rest of the flow are just standard OAuth parameters. Code verifier, and so on and so on. Good. Number 4, no details there. That's something that the STS has to do. You have to verify the signature on the Deop Proof, make sure it corresponds to the request and that the embedded public key makes sense, and so on and so on. So a lot of checks have to be done correctly. Now we generate the tokens. We're going to include a CNF claim, confirmation, just like before, but no longer an X509 certificate thumbprint, but a JKT, a JSON Web Key thumbprint. Now this is the fingerprint of the public key that has been included in the token, in the Deop Proof earlier. All right, as stated here on the slides. Good. The response to the client is a normal response, traditional tokens being sent in the JSON response there, nothing special going on. Now we want to call the API. What do? We generate another Deop Proof. You can kind of see where this is going, right? The Deop Proof, what it will contain. It will contain the same parameters as before, like the type and the key from the client, but also the specifics about what we're calling on the API. So you can see on the bottom here that we have, again, a unique identifier. We have the HTTP method is included, a GET request to a specific API endpoint. This links that proof to that one request. Otherwise, if the attacker would capture one proof and it's valid for all API calls, then they can just call whatever they want. So this wouldn't make any sense. So again, there's an issued at timestamp, but there's also a linkage of this proof to a specific API endpoint with a specific HTTP method. All right, and then the unique identifiers, the GTIs, are in there to prevent replay attacks. So the attacker would be able to replay the exact same request, but because of that unique ID in the GTI claim, the API should be able to reject it. Should be is a very big importance nuance here, because of course it depends on how the API handles this, but this is what should happen in practice. All right. Additionally, the access token itself is linked to this proof, so you can't use it with different access tokens either. It has to be used with this particular access token. All right. And of course, it's again signed by the client's private key. Request goes out. What does that request look like? Final monospace slide, so enjoy it. This is basically a request to the reviews endpoint on the API. It's a GET request, like in the proof. There's a DPoP header with the proof. And there's an authorization header with our token, and the type of the authorization header is no longer bearer, but it's now DPoP. That's a big change. Telling the API this is a DPoP token must follow all of the DPoP verification steps. That's essentially how this works in practice and what you can find there in case you're looking at a PDF instead of an audio-based version of this presentation. All right, verifying the Deop Proof on the API side. This is fairly complex. I'm not going to go into details here. There's a whole bunch of steps you have to follow, like check the signature on the job, check the payload that it corresponds to the API call, make sure that the access token used matches the hash in the Deop Proof, and so on. As you can imagine, this is something that you have to implement with a lot of care or use libraries that support this. All right, and that is basically how we can use sender-constrained tokens. This is a recommendation, something that you actually should be doing for a whole bunch of OAuth applications, not like the simple public stuff that nobody really cares about, but any sensitive business application could really benefit from sender-constrained tokens. But it is a bit more of a heavy lift than tweaking some parameters in the authorization request. It requires key management and proof generation or MTLS and so on, so it is a lot more effort. But if you're building something sensitive, strongly consider proof of possession mechanisms for your tokens. Let's get rid of bearer tokens, which is kind of a slogan that has been circulating in the community for like 12-ish years. So let's get rid of bearer tokens, and here we are. All right, that was kind of a wild ride. Hope you enjoyed that. Hope this was useful. I'm gonna narrow it down to 3 key takeaways about the 3 topics we talked about, not surprisingly. Use resource indicators to reduce the authority of your access tokens if you are dealing with access tokens from multiple APIs. Use PAR, absolutely recommended. Big, significant security benefits, also makes your deployments easier and so on and so on. Definitely consider using PAR if your STS supports that, and use sender-constrained tokens over bearer tokens. It significantly increases security, and it can really help you lock things down. All right, thank you very much. I hope you enjoyed it, and now I have time for questions if you have them. All right, that's the best kind of question, the one that has already been answered. Awesome. There's more.
What's the benefit of using resource indicators instead of just different access tokens or like different flows per API?
The benefit is that you don't have to run multiple flows. You can run one flow with all the resource parameters up front. The user will be prompted once for consent if consent plays a role, and then afterwards you can just in the background request what you need token-wise. So yeah, exactly that. Might also be useful for offline scenarios where the user is present once, you run the flow, you ask permission to access 5 APIs, and then with a refresh token later on, like 2 days later, you can get an access token explicitly for that API, which otherwise would be hard unless you have to run all the flows sequentially up front and so on. So yeah. Anything else? No. I don't do .NET, so no, go ahead.
This is not a .NET question, but if you use DPoP and resource indicators, would the refresh token usage also require DPoP?
It depends, I think. So you can use DPoP for refresh tokens as well. So in that case, the refresh token will be bound to a specific key held by the client. I don't have a concrete answer for you right now because I would have to look into that, because using a refresh token already requires client authentication, so it's a form of a sender-constrained token, not proof of possession, but client authentication based. So I'm not sure if in this case there would be a lot of benefits for that, but
I'm going to say something ugly now. If you would use refresh token in a browser context without
no. There's an OAuth spec detailing how to do OAuth in browser-based applications, and it basically says don't do it. I know because I wrote that part in there. No, so if you're doing OAuth in browser-based apps, I did a talk about that a year and a half ago at NDC Security, so check that one out. It's on YouTube if you want to. You should use a BFF, and it's a backend client at that point. So with all due respect, but I'm not going to talk about refresh tokens in browsers because it's a bad idea. So even with DPoP doesn't really help there at all. So yeah, it makes it more complicated, but it doesn't add security in that case. Other questions? All right. In that case, feel free to stay and enjoy the air conditioning, and enjoy the rest of the conference.